So here's part 1 of chapter 21 lecture, carboxylic acid derivative. Here are acid derivatives, acid halides, anhydrides, esters, amides, and nitriles. All the derivatives can be converted to carboxylic acid by ester or basic hydrolysis. Esters from carboxylic acids are generated from the reaction of acid and alcohol in acidic conditions to generate your ester and water. This is Fischer esterification, and in order to drive this reaction, excess alcohol is added. Nomenclature of esters. Esters are named alkyl carboxylates. First word is derived from the alkyl group of the alcohol, second word from the carboxylate group of the carboxylic acid. So I'm just going to pick two examples. Here's phenyl benzoate, right? This would be benzoate, and then this is the phenyl part. This will be cyclopentane carboxylate, and then this would be methyl, so it would be methyl cyclopentane carboxylate. Cyclic esters, you can have an esterification reaction with the OH and COH. On the same molecule, this would generate what is called a lactone. To name it, the word lactone to the IUPAC, add the word lactone to the IUPAC name, or replace it with ic acid with a common name, O-lactone. Just going to focus on the IUPAC naming system, so this would be 1, 2, 3, 4, 5. So this is a pentanoic acid lactone, and it would be 5-hydroxypentanoic acid. And here, this would be same 5-membered, so it's a pentanoic acid lactone, but it's a 2-methyl 4-hydroxy so it's 4-hydroxy 2-methyl pentanoic acid lactone. Amides, you take an acid and your amine. This will generate a salt, and then under heat will generate your amide and water being expelled. They're not basic because the lone pair of the nitrogen is delocalized by resonance, and the CN has a double bond character. Here's the example of the reason why you have a double bond character, because you have resonance, right, shown here, and then this generates this. When you have acid or concentrating protons or concentrating acid being added to the system, it will protonate only on the oxygen, right, and not on the nitrogen. Classes of amides. Amides, primary amide, secondary amide, and tertiary amide. Secondary are also known as N-substituted, and tertiary are N-substituted amides. Nomenclature of amides. So for primary amide, you drop ic or oic acid from the carboxylic acid name and add the amide. And so here are examples. This would be 1, 2, right? So that's ethyl at the N position, so it's N-ethyl. And then this would be ethane amide, so it's N-ethyl ethane amide. And you can go down these examples. Alkyl groups bounded to the nitrogen are named with an alkyl, as I've shown here, to indicate the attachment to the nitrogen. You can also have cyclic amides. When they're cyclic amides, they're called lactams. To name, you add the word lactam to the IUPAC acid name or replace ic acid with common name O-lactam. So here's an example. This would be 1, 2, 3, 4, right? So it's 4-amino and butanoic acid lactam. And you can do these examples as well. Nitriles, hydrolysis to the acid. You can take nitriles, water, and either in the presence of acidic or basic conditions, this will generate a primary amide, so you can reduce that down. If you have water again under acidic conditions, you can get it all the way up to an acid. If we look at the structures of acetonitrile and propyne, right, they're the same except you have C triple bond N and C triple bond C. Both compounds, atoms at the ends of the triple bond are sp hybridized. Bond angles are 180. In place of the acetylenic hydrogen atom, you have a lone pair of electrons, and that's in the sp orbital of the nitrogen. And the non-bonding electrons of the nitrogen over here are not basic. That's a note. Synthesis of nitriles from acids. You can take an acid, reacted with ammonia and heat, right here, electrons come up, tetrahedral intermediate, and this gets kicked off. Once you generate your primary amide, you can react it with POCl3, which is a new reaction for you guys, and this will dehydrate to form the nitrile. Naming nitriles, so for IUPAC names, which is what I'll hold you to focusing for your exams, you add nitrile to the alkane name, and the ethyl octanoic group can also be named as a substituent. The cyano group. Common names come from carboxylic acid replacing ic acid with O-nitrile. So this would be ethane nitrile or commonly acetonitrile. Here it's 1, 2, 3, 4, so it's butane nitrile, but it's 3,3-bromobutane nitrile, and etc. as shown here. Acid halides, essentially instead of the OH you have a halogen attached, and so this is an acid halide or acyl halide, acid chloride, acyl chloride, acid bromide, acyl bromide. So acid halides are called acyl halides. They're more reactive than carboxylic acid, so they're used to synthesize other acid derivatives such as esters and amides, and their most common one is a chloride. Acyl halide nomenclature, you essentially name by replacing ic acid with il and then the halide name. So instead of ic acid, it's now ethanoyl, right? So il instead of ethanoic acid, and then you add fluoride. And so you can go down through the series. Acyl chlorides are most common. Acid anhydrides, if you take an anhydride reacted with water, right, your electrons are from the oxygen of the water, electrons will come out forming tetrahedral intermediate, those will come out and kick off to form the carboxylate, and then get protonated later on. You can generate 2 molecules of acid when you react it with the anhydrides. A thing to note for the previous case, or this acid anhydrides, is that acid chlorides are more reactive than acid anhydrides. So here's your mechanism: nucleophile attacks, electrons go up, this forms that tetrahedral intermediate, electrons come down, kicks this off, forming the carboxylate and your product. So anhydride nomenclatures, if we look at how these are being named, essentially they're like the acid, but the acid is then replaced with anhydride. And then for mixed anhydrides, you just name both acids. So here, these are all actually symmetrical anhydrides. So let's take a look. This would be ethanoic, right? Ethanoic, and then anhydride instead of ethanoic acid, and etc. You can do the rest as examples. Multifunctional compounds. So the functional group with the highest priority determines the parent name, and the order goes acid, then followed by ester, amide, nitrile, aldehyde, ketone, alcohol, amine, alkene, alkyne. So this is something that you should definitely know or memorize. So if we look at this, you have a nitrile versus an ester. So this is a priority. So this is now going to be named as an ester. So it's going to be this part and this part being the ethyl group, right? And then the carboxylate group. So it's a ortho, right? Cyanobenzoate. So it's ethyl ortho-cyanobenzoate. And you can do the same thing with these others by going through the list and figuring out what the priorities are. If we summarize the nomenclature, carboxylic acids, if it's in the main group, then it's going to be oic acid, or if it's a substituent, carboxy. Esters would go as OAtes or alkoxycarbonyl. Amides are amide or amido as a substituent. Nitriles are nitriles or cyano as substituent. Aldehydes are al or formyl as substituents. Ketones on or oxo as substituents. Alcohols all. Hydroxy as substituents. Amines or amino as substituents. Alkenes are enes or alkenols as substituents. alkynes, ines, or alkynals. As substituents, alkanes, enes, alkyl as substituents. For esters, it's an alkoxy, and for halides, it's a halide. In terms of boiling points of carboxylic acid derivatives, amides are the highest boiling points, and primary amides are higher than secondary, then tertiary. These are then followed by the carboxylic acid series, then followed by nitriles, followed by alcohols, and then you have kind of the methyl esters, and then your alkanes and acid chlorides, sort of on the same line. Intermolecular forces. So in amides, resonance pictures shows that they're highly polar. As a result, they hydrogen bond, and they'll result in higher boiling points. Melting points. Amides have high boiling points and melting points compared to compounds of similar weight, and the melting points increase with increasing numbers of NH. So the primaries, or the non-substituted amides are going to be the highest, followed by the N-methyl or the dimethyl, as shown here. In terms of solubility, acid chlorides and anhydrides are too reactive to be used with water or alcohol. Esters, tertiary amides, and nitriles are good polar product solvents. Solvent commonly used in organic reactions are ethyl acetate, dimethylformamide, and acetonitrile. Here are the examples and pictures of those common solvents. Here's ethyl acetate, DMF, dimethyl acetamide or DMA, and acetonitrile shown here. And their boiling points, melting points, and solubility in water. This is in your book, Table 21-2. Nucleophilic acyl substitution. Interconversion of acid derivatives occurs by this nucleophilic acyl substitution. Your nucleophile adds to the carbonyl, forming a tetrahedral intermediate. Elimination of the leaving group regenerates that carbonyl. This is also known as addition elimination. Nucleophilic acyl substitution are also called acyl transfer reactions because they transfer the acyl group to the attacking nucleophile. Mechanism. The mechanism is your nucleophile attacks. Electrons go up. This forms that tetrahedral intermediate. Then your electrons from the oxygen come down, kicking off your leaving group, and that's it. The thing to note is that this mechanism is general, and it applies to most of the reactions in the reactivities. So acid chloride is most reactive, followed by anhydride, then esters, amides, and then carboxylates. And then in leaving group, the counterpart, so the chloride is less basic, but as you're going down this, you're getting more basic. Interconversion, again, acid chloride can convert everything. Can be converted into anhydrides, esters, amides, or carboxylates, and then carboxylates can be reacted with SOCl2 to generate the acid chloride. Anhydrides can only form esters, amides, and carboxylates. Esters can only form amides or carboxylates, and amides can only form carboxylates. Acid chlorides to anhydrides. Here again, your acid reacts, nucleophilic attack, electrons go up. This is your tetrahedral intermediate. Electrons from the oxygen come down, kicking off the chlorine. Leaving group, this will deprotonate, neutralize the positive charge, generating your anhydride as well as HCl. Acid chloride to ester, again, nucleophilic attack, electrons go up. This forms a tetrahedral intermediate. Electrons from the oxygen come down, kicking this off. Almost there. This is still protonated. The chlorine will then deprotonate, neutralizing it, forming the ester. In terms of acid chloride to amide, your amine reacts, kicking out electrons to the oxygen. Now the electrons from the oxygen come back down, kicking off the chloride. And rather than the chloride coming and deprotonating, your amine comes in, deprotonates, neutralizing it, forming the chloride salt and your amide. So ammonia yields a primary amide, secondary amide, tertiary amide. Anhydrides to ester, your alcohol attacks, electrons go up, tetrahedral intermediate is formed, electrons come back, and then electrons go to form the carboxylate. Once the carboxylate's formed, you have deprotonation, generating your ester and your acid. Anhydrides to amide, your amine attacks, right? Electrons go up, forming that tetrahedral intermediate. Electrons come down, kicking off the electrons to the oxygen, forming the carboxylate, and that carboxylate will deprotonate, neutralizing it, forming the amide and the acid. Again, ammonia will yield the primary amide, primary amine, secondary amine, tertiary amide. Ester to amide, ammonolysis. Here's your primary amine, attacks, electrons go up, forming that tetrahedral intermediate. Electrons come down and kick off electrons to the oxygen. Your alkoxide will deprotonate and neutralize that positive charge, forming your amide and alcohol. In this case, your nucleophile must be NH3 or a primary amine, and you're going to need heating in order for this reaction to here, when you form your amide, your alkoxide is there, and that alkoxide is formed. It's a strong base, and it's not usually a living group, except in an exothermic step, of which this is. So if we look at our energy diagram, you have your first step, your tetrahedral intermediate, forming your amide. It's still protonated, and then forming the neutral version. So here you're going to have transition states for each step, between the steps, and your rate limiting step is over here, where your transition state is when the bond is about to break to form the methoxide. This elimination of this alkoxide is highly exothermic, right? And so, so you can introduce heat in order for this reaction to move forward. A thing to note is that a strong base can serve as a leaving group if it leaves in a highly exothermic step, usually converting an unstable negative charge intermediate to a stable molecule. Transesterification, so you can have your ester and a large excess of your alcohol, either under acidic condition or basic conditions, will generate your new ester. So one alkoxy group can be replaced by another in this transesterification, either through acid or base catalyst, but a large excess of this alcohol is required for the stir. If we look at an acid-catalyzed transesterification mechanism, first part is protonation, then your alcohol comes in, attacks, forming the tetrahedral intermediate, then another alcohol will deprotonate, forming the neutral versions. So now that's all neutral, your leaving part will then protonate, forming a good leaving group. Then electrons from your oxygen come down, this will get kicked off, and then you deprotonate to neutralize your new ester. If it's base catalyzed, it's much easier. You just have direct nucleophilic attack, forming the tetrahedral intermediate, and electrons come out and just kick off the alkoxide. Hydrolysis of acid chlorides and anhydrides, you have water attack, electrons go up, forming the tetrahedral intermediate, electrons come down, chlorine gets kicked off, then the chlorine then deprotonates, generating the acid and HCl. So because water can attack acid chlorides and hydrolyze, if you want to protect that from hydrolysis, you want to protect it from any type of moisture to maintain the acid chloride. Here's the hydrolysis of esters, also known as saponification. Your hydroxide comes in, so it's under basic conditions. Electrons go up, form the tetrahedral intermediate. Electrons come down, forming the alkoxide, and the alkoxide will then deprotonate, forming the carboxylate and alcohol. This is also known as saponification, and saponification means soap making. So this ends part 1 of this chapter.